Okay, these are a couple of examples then that'll help you understand single slit diffraction and thin layer diffraction. So let's say we have light of wavelength 600 nanometers is incident upon a slit, a single slit of 0.255 millimeters. And there's a wall or a screen that's 2 meters away from the slit. So what are we finding? For a single slit, we're trying to find the location of the first dark. So this is the 0 bright. This is dark 1. And there's a dark 1 on the other side. And there's a dark 2. And a dark 2. This, of course, is bright 1. And this is bright 1. Okay, bright 1's located right here. This would be bright 2. And this would be bright 2. So what are we going to do? We're going to use the equation A sine theta equals m lambda. And again, m is going to equal 1, 2, 3, etc. Different than double slit, m starts with a 0, okay, for double slit. Okay, so let's go ahead and use this equation then. I'll do it over here. So we have A, which is in millimeters, so it's going to be 0.000255 sine of theta is equal to m, which is 1 times lambda, and that's 600 times 10 to the minus 9. Okay, once we do the inverse sine on that, the angle theta comes out to be equal to 0.135 degrees. So a very small angle. Okay, so that angle is this right here. I'm just going to draw an arrow to it. It's the angle mapped by this 2 meters and this y, and there's your hypotenuse. What we want to find out is what the y location is. So now I'm going to say tangent of 0.135, okay, is going to equal, okay, it's going to equal opposite over adjacent, y divided by 2. And once we find out what y equals, y is going to equal 4.7 millimeters. Okay, so I'm just going to locate that here. I'm just going to write like 4.7 here. There's another one here, 4.7, if you want to call that minus 4.7. And that's measured from this 0 line here. So it's 4.7 millimeters away. So the next one will be twice that. So that's going to be 9.4. So located right there. Okay, and then we can keep going with that. We can map all the darks. I've only mapped 2 here. Okay, so where is the distance going to be located for the brights? Well, they will be halfway in between there. Okay, and that's going to be, for this bright, we'll just kind of draw a little dash line here. That's going to be about 7.1. And then down here, it's going to be another 7.1. That's approximation there. Okay, it's going to be whatever halfway in between those two is going to be. So that's how you do single slit. You map all the darks, and then you locate halfway in between what the values would be for the brights. For double slits, it's easiest just to map all of the brights and then locate the darks halfway in between. Okay, let's go on to thin layer interference. So let's say I've got light of 600 nanometers that's incident upon a system that we have here. The first is air, and then we have another layer which is oil, and then water. So let's say we're looking at a thin layer of oil, okay, that's resting on top of water, and that will cause a thin layer interference pattern. So let's take a look. So light ray coming in is incident upon our oil. We notice that the oil is in the fraction 1.4, which is larger, okay, than the 1.00 of air coming in. So we know this one here will be 180 degrees out of phase. So I'm just going to label that 180 degrees out of phase. This light ray, of course, is the refracted one. It goes in. It's not 180 degrees out of phase here. It's incident upon this side here, where water is 1.33, which is less than the oil. So it's going to be reflected back, still in phase. There will be no 180 degrees phase shift there at all. It's then going to get refracted out. Still no 180 degree interface change, because that's simple refraction. And then these two light rays are going to interact with each other, overlap each other. And since this ray is out of phase and this one is not, it'll make a dark So it's going to make a dark band. So then I'm going to use my equation. 2nt equals m lambda. Okay, and I want to solve for the thickness of this oil band, which will produce a dark band pretty much right at the interaction point where these two light rays are interacting. And that means if your eye is looking on top of here, it's going to interact pretty much right above here. Okay, I'm going to choose m equal 1. I always want to choose the first band because my eye is looking pretty much right down on top of this. There are other bands going down here, but then I don't know how far away that is. So I just want to be simple here. So then my equation is going to be 2n, which is 1.4, times t, which I don't know what it is, equals 1 times 600 times 10 to the minus 9. And solving for t, I get 2.14 times 10 to the minus 7 meter thickness. Okay, so about 2/10 of a micron, or 2/10 of a micrometer thick is what we're looking at there. Okay, so what does this mean? So a thickness of a layer, about 2.14 times 10 to the minus 7 meters. If the layer is that thick, if my eye is looking over this, I will see a dark band pretty much right over where my eye is. And of course I'll see lights and then darks, lights and darks, lights and darks. Now if I wanted to locate the first light band instead of the first dark band, then I would use the m plus 1/2, okay, times lambda for this equation. But typically what I do is I only use this equation here to locate either the bright or the dark, and then I know the other one will alternate in between what I'm looking at. And that's how I do thin layer interference.